Hello everyone. Today we will solve a problem related to geometry in which we are asked to prove some properties about a special point inside a triangle. This problem is from fortnight 8 of SuMON program, and let's get into the problem. Consider an acute angle triangle ABC. So let's consider some triangle like this. Construct equilateral triangles on the sides of the triangle. So let's do that. Let us move the triangle slightly down and then let us construct the equilateral triangles. The equilateral triangle on side AC would be like this and on BC would be like this. Though they are not very precise, they can be close to precise. And on AB, it's a smaller one because AB side is smaller. The vertex of the equilateral triangle on side BC is X, whereas on AC it is Y and AB it is Z. Let's name them. And remember that these should be constructed outside the triangle. So these are equilateral. Let's use the style on the lines to represent this. This is given a style 2 and this is given a style 3. Now, prove that the lines AX, BY, CZ concur and such that their lengths are all equal to the point of concurrency P to the three vertices of the triangle. So the diagram should look like this according to the proof. AX, BY and CZ should all pass through a point P, and this was the special point that I was talking about. And it turns out that the length of AX equal BY equals CZ, which equal the sum of distances of P from the three vertices of the triangle. So I will give you more insights about this point and its name at the end of the video. But let's prove this at first, because this will help us in proving some more special properties. And you will also be given with exciting homework at the end of this video. So at first, let me only construct the BCX equilateral triangle, which looks like as follows. We have ABC, onto which we decrease the size, onto which I have the equilateral triangle BCX. First, realize that AX should lie between the lines AB and AC. Kind of like AX divides the acute angle BAC. This is due to the reason that triangle ABC is acute angled. Because if AX were outside, then the diagram would look like this. Here is the ABC triangle and here is the point X. And if X is going to be in this configuration, then we can see that this angle, which is supposed to be B plus 60 degrees, is going to be greater than 180 degree. That implies B is greater than, the angle B is greater than 120 degrees. But that's not true. We are considering acute angle triangle here, right? So X cannot lie in this configuration. So AX should divide the acute angle BAC. So this is the first observation that comes by virtue of the condition acute angled. Next, let's construct the circumcircle of triangle BCX. You would observe that it intersects the segment AX at Q, which is inside the triangle. But why should this be the configuration? We should consider this as the configuration because at first realize that the segment AX and BC intersect as AX lies between the lines AB and AC. That means when you draw the circumcircle of triangle BCX, definitely the chord QX of the circle should intersect the chord BC of the circle. That means Q and X lie on opposite side of chord BC. Alright. Now why should Q lie inside the triangle? Why can't it lie outside the triangle like here? It is now due to the fact that the segment which is above the side BC of AX is entirely inside the triangle. And remember that angle A is less than 120 degrees as it is acute. That means the point A cannot come inside the circle as the circle is the locus of points that make equal angle. So this angle would be 120 degrees and point A cannot come inside, otherwise angle A would be greater than or equal to 120 degrees. Thus, point Q lies on the segment of AX which is above BC. That means it is inside the triangle. So these are some configurational considerations which is essential to solve this problem. Alright, let's join QB and QC. Notice that angle XBC is 60 degrees and by inscribed angle theorem, angle XQC is also 60 degrees. So we know that this is going to be the configuration and hence B and Q lie on the same side of the chord CX. So angle XQC is also 60 degrees. That implies angle AQC is 120 degrees. So let's consider the angle AQC. This is also 120 degrees. Now notice that the points A, Q, C and Y are concyclic. This is due to the fact that opposite angles add up to 180 degrees. Notice that if I construct this equilateral triangle, which is ACY, then angle AYC would be 60 degrees and 120 plus 60 is 180. That means these 4 points are concyclic. And similarly, AQB is also 120 degrees, which is here. And thus, the points AQBZ are concyclic due to the fact that opposite angles are supplementary. So we can see that all 3 circles pass through this point Q. Alright, so how will I now prove that AX, BY, CZ all concur? Now it is just extension of the line BQ and CQ. You will realize that when BQ is extended, extend BQ and you will see that it will pass through Y. Because when you join YQ, I know this angle would be 60 degrees. And that means 60 plus 120 is 180. Thus angle BQY is 180. Angle BQY equals angle AQB plus angle AQY. But AQB is 120 plus AQY is 60 by inscribed angle theorem, which sums up to 180 degree. Therefore, BQY forms a straight line and BQY are collinear. So BY passes through Q and similarly, CZ also passes through Q. Thus, we can say that AX, BY, CZ concur at Q. So this point is regarded as P in the question. But now, coming to the lengths, how are the lengths related? So let's go to the triangle BQC and consider the cyclic quadrilateral BQCX. So let me draw it separately. If you consider BQCX, I know that it is cyclic quadrilateral. Thus, their lengths are related with Ptolemy's theorem. And remember that BC, let's call it as A, let BC equal A, and BX and CX will also be A because it's an equilateral triangle. And Ptolemy's theorem states that by Ptolemy's theorem, it is known that the product of opposite sides, the sum of product of opposite sides equal the product of its diagonal, which is QX into BC. I know BX equal A, CX equal A and BC equal A. So all 3 are equal. Thus we can cancel out to give us QX equals BQ plus QC. Now let's add AQ to this. AQ plus QX equals AQ plus BQ plus CQ. But AQ plus QX is AX. Thus we have proved that AX equals AQ plus BQ plus CQ. Or we know Q equals P. Thus it is AP plus BP plus CP. So with the help of Ptolemy's theorem, we have proved that AX equals this length. And by similar Ptolemy's theorem in other cyclic quadrilaterals like AQCY and AQBZ, we can easily get that CZ equals BY equals AX equals QA plus QB plus QC. So thus we have proved the question. But what else can we derive from here? we can derive that the sum of length of Q from the vertices is minimized at this point. Why should this be minimized? It is due to the Ptolemy's inequality. So applying Ptolemy's inequality on any point T with the triangle BCX would give us BX into TC plus CX into TB equals TX into BC. But again, I know that BC equals BX equals CX. So I can cancel that out, implying that TC plus TB equals TX. And if you add up AT to this, you would get AT plus BT plus CT equals CT plus TX. But remember, now point T is a random point. So we cannot use equality, we should use inequality, that the sum of product is greater than or equal to the product of diagonals. And equality holds if point T lies on the circle, the circumcircle of BCX. Thus you would have inequalities like this. And again, CT plus TX is greater than or equal to CX. So here it is AT, and AT plus TX is greater than or equal to AX. And now I want the sum of distances from T to ABC to be minimized. Thus, we should have the two inequalities to hold true, to turn to equality. And that happens when the point T lies on the circle, the circumcircle of BCX, and also that points A, T, X are collinear. And that happens when T is the intersection of AX with the circumcircle of BCX, which is equal to the point P that we were discussing. And this point has a special name called as the Fermat's point. The Fermat's point, or they also call it as Torricelli point. So for acute angle triangle, thus the sum of distances from the Fermat point to the vertices is minimized, and it also equals the distance AX and also equal to BY, also equal to CZ. So as a homework, think about the possibilities if the triangle is obtuse, and you can comment your ideas in the comment section below. The boardwork will also be given in the description. You can download it there. See you all in the next video. Keep doing great mathematics. Thank you.